Okay, so thank you everybody for being patient and tolerating this this teleconference. I think we're all going to have to get a little bit used to this style of interaction for a while. Hopefully it won't be too long, but so it's good to have practice. I'm actually at my home because my daughter's sick, so we have got a little bit of extra complication too. So what I want to say is that with this this format, I really dislike giving teleconference kind of talks because you don't get any feedback from the audience and it's hard. So feel free to interrupt me, and if someone's trying to interrupt to ask a question, try and help them get the attention so that I can answer that question. I don't mind at all getting interrupted. I would much prefer that what I'm presenting is clear to you guys, and that if you have any questions that you ask them. And I also, we'll see how this works, but you know, a couple of the things that I'm going to talk about, I'd like some audience interaction to get some input. So if that doesn't end up working very well in this context, then we'll just, I'll just not try it, but that's what I intend to do. So as Liliana said, my training is in psychology, and that's a typical human factors training. There are also lots of engineers who have an interest in how humans interact with things, and they, you know, the human factors is really the intersection of psychology and engineering, and also lots of other disciplines. Looks like the bio I sent to Liliana was a little bit outdated. I've been working at the lab for 10 years now, and I have very diverse research interests. It's all how humans interact with systems. And a lot of my cybersecurity research has focused on how to characterize risk to systems. And what I find really interesting is that people tend to ignore humans. This is the soapbox part of my talk, because humans are hard. It's hard to predict what we do. It's hard to measure our behavior. And we don't really understand a lot of the underlying principles. We have a lot of, you know, sort of high-level decision-making biases that we can characterize pretty well. And in some cases, we can predict human behavior, but it's highly variable. Individual differences matter quite a lot. And so it can be extremely challenging to characterize how humans are going to behave in a system. On top of that, I think humans are also the most important part of the system, because they, first of all, we design systems for humans. And the way that we behave really influences how the systems behave. And as I'll get through, the assumptions we make and whether those assumptions remain valid across different contexts matters a lot. So, you know, as people who are in a technical field, I always try to encourage people to really think about how the humans fit in, how they interact with systems, what assumptions we're making about how they're going to behave, and how we're supporting humans in a system as well. So that's the soapbox talk as I go on. So just to start, we're going to talk about security. So I just kind of want to ask some questions about what it means to be secure, because that's what people are after. Like, I want my system to be secure. So are your homes secure? And how do you know? So can I get a volunteer to just describe how they secure their home and what factors they consider?
Anyone? Yeah. Lock the door. Lock.
Yeah, okay, so we lock the doors, right? So what is that protecting us against?
Intruders.
Intruders, and what are intruders going to do when they get in?
Steal stuff.
Steal stuff, right? So that's one thing. So we make the assumption that one of the reasons that we protect our homes is so that we can protect our stuff. Is the door an effective control against that?
It's a deterrent.
It's a deterrent. How do you know that it's an effective deterrent?
It's not worth the effort sometimes.
It's not worth. So okay. So those are, you know, all reasonable answers. So can someone help me unpack the assumptions that are going into all of that?
You're assuming someone wants to break in your house and steal your stuff. You're
Right.
locks on your doors will work or deter the person who wants that.
You assume that the mode of entry they're going to use is the door.
Exactly. What else?
You also
You're assuming, go ahead.
they're not motivated enough to find a real way in.
Yep. And those are all exactly, I mean, those are all the kinds of things that we assume, and it seems kind of silly for a house, right? But what if you're protecting against what if you just want to make sure that your family's safe? Would different assumptions work? And I think the biggest challenge is that when you talk about computer security, especially for critical systems, people make those assumptions, right? So we have these like sort of common sense barriers. We have the door, we have the door lock. Door locks are extremely easy to a typical door lock is extremely easy to compromise if you are at all determined. And similarly, a lot of the security controls we put into place, some of the common sense controls for a determined intruder would be extremely easy to compromise as well. And so, you know, for our homes, we can't say that our homes are secure. Because, you know, I'm making the assumption that, you know, with that no one's going to try to break down my door or going to enter through the windows because most of the people are maybe opportunistic thieves. When I was talking to my husband, who's a cybersecurity researcher, who has Robert Urbis, who has sort of influenced a lot of my thinking in this area about, you know, the assumptions we make in Idaho Falls, which is a relatively small and safe community, versus the assumptions we make in Albuquerque, New Mexico, where we both lived. And here we can kind of assume that our stuff is safe pretty much all the time, no matter what we do. And that has sort of borne out in our experience here. However, in New Mexico, we could not assume that our stuff was safe, even if we had it locked in our garage. And so it was far more likely that someone was going to come in and try to steal a bike or something, even through a locked door. And actually, we had our appliances stolen from a house that was vacant when we moved to Idaho Falls in Las Cruces, New Mexico. And you know, we sort of assumed that everything was safe in there, and why would anyone steal an appliance? And so all of those things go into our assessment of whether we're safe or not. And the bottom line here is security is not a thing that just exists. You can't be secure or not secure. Security is always in relation to other factors. So what are you securing against? What are you protecting, and what are you protecting it from? And are you making assumptions like my lock is going to work? And I think this gets even more challenging as you talk about technology, because technology can be compromised in different ways than we're used to. And I think most importantly for me is humans define the context. The world doesn't care about security. The natural world, the physical world, the technological things that we design and build are all designed by humans. We define the context. Obviously physics exists, but we're designing and interpreting around it. So any questions or comments that anyone wants to make? Excellent. So, and humans are they are around through the entire life cycle of the system. So if I'm designing a nuclear power plant, which is what I'm going to talk about today, or an airplane, which is also another interesting case study if you're talking about the 737 MAX accidents, that this is essentially an extremely compelling example of what I'm talking about. And if you want to learn more about that, I have a talk that I can share with you guys, and a paper that describes that. But that's an extremely compelling illustration of this. So when someone's designing a system, they make assumptions about the context in which it's going to operate. They make assumptions about how it's going to be operated. You assume like what the physical constraints are. We use our understanding and knowledge of physics to design something, but that's interpreted through our human understanding and knowledge. And so, you know, some of the things, the physical phenomenon that we're trying to control are extremely well understood, and some of them are not. And so we sort of interpret what those, what the physics actually mean in the context that we're doing it. And then we actually build the system. And, you know, you have the design intent, and then you have the actual implementation. And this is where one of the things fell apart in the 737 situation, is because you had a design and it was not implemented as intended. And so that implementation, you could have the human interpreting what the documentation was. There could be documentation missing. Someone makes some assumptions about what the designer meant. And then, you know, you just have human error. So someone can just simply make a mistake. And then once you've designed and actually constructed a system, you often have additional things like you configure the system, you set it up, you actually implement security controls if you're talking about cybersecurity, and those are all done with humans. And configuration is actually where a lot of human error comes into place, because sometimes the documentation is not all that well understood. You make some additional assumptions about what the system is going to do. And finally, when you're operating the system, you're essentially building all of those previous stages. You know, you have the information that is used to operate a system is, you know, it's carried to the operator through all of the decisions the other person made, and that the operator has their own human error possibilities. They also have their own interpretation and assumptions that they're making about what the system is doing, training, background experience, previous experience, administrative controls, procedures, all sorts of things influence how the operator is going to behave. And all of those things carry with them some possibility of misinterpreting information or just having an error. And this is overly simplified. It's far more complex than this. And there are interactions between all of these different stages. And the bottom line for this is that each stage we make assumptions, we interpret the information, and whether those assumptions and interpretations are valid is where I think security risk occurs, where I think all risk occurs, but particularly security risk, because when we talk about security, we're talking about what are we trying to protect in our system, what's important in our system, and how effective are the controls that I put in place or the mitigations to actually prevent whatever I'm trying to prevent. So does anyone have questions at this stage or anything they want to add? Okay, I will move on. I'll try to pause long enough for people to jump in. Okay, so in the room, how many of you are familiar with nuclear power or how it works?
A little bit.
Can I get it? Does anyone in the room have familiarity?
Yeah.
Okay. Okay, so it's not going to be like, it's not going to be overly simple to just explain the basic principles. Can you guys see my cursor?
Yes. Yes.
Okay, so nuclear power, the way I describe it is it's a fancy way to produce steam. That's the only thing. Once you've got steam, a lot of the power plant works exactly like a similarly designed steam plant that uses coal to create steam in it. The kind of nuclear power plant that I typically work in is, or not work in, I don't work in a power plant, but work with, is a what's called a pressurized water reactor. So the special part about a nuclear power plant is getting energy from nuclear fission. You have the unstable isotope of uranium, typically, is what the fuel is used. That is, when it's hit with a neutron, it tends to split because it's unstable. When it splits, it, obviously other daughter particles and atoms, but the things you're interested in are the heat and the fact that there are additional neutrons released, which can drive what's called a chain reaction, which can be sustained over time. And sort of self-sustaining so that you can continue to release heat from splitting the atom. And so that's it in a nutshell. It's far more complex than that. And people's whole careers are devoted to characterizing how this works. But this is where we're interested in the heat. We're interested in the number of neutrons that are available to drive that heat. We call, just high level, call that reactivity. As long as the chain reaction is very well controlled in a nuclear power plant, it's not like a bomb. You can't get a sort of uncontrolled chain reaction in the conditions that we have in the fuel and in the system. It just won't happen. And so one of the things that nuclear power plant operators really care about is maintaining that control of reactivity, the number of neutrons that are available to drive the chain reaction. So this happens in what's called the reactor core, which is in a pressurized vessel. That pressurized vessel is also isolated, and so it's a closed loop. So here where we have this red bit of water circulating, we have the reactor fuel down here where we're creating heat. We have these control rods, which are typically, they're made up of a material that absorbs neutrons. So we can control how many neutrons are available for that chain reaction. To put the plant in a safe state, we do what's called a reactor trip, which drives these control rods all the way down into the bottom of the fuel. And the intent is to absorb all the neutrons so that you can no longer have a chain reaction, which means the plant is shut down. That is one of the main safety functions of a nuclear power plant. The other safety function is providing cooling to the system, because you don't want to melt the fuel and you have to remove heat from the system. So normally we want the heat because that's what we are using to generate electricity. So the way the system works is that the system that's under pressure circulates water. It has a connection to what's called the steam generator, and the steam generator is where the scenario that I'm going to show you is where it happens, the control of the level in that generator. And so this is why I'm describing this just general nuclear power. So what we have here is we have tubes that have hot water on one side, cold water on the other side. The system is not under pressure, so when the water is heated, it turns to steam. That steam turns a turbine, which generates electricity. And then that steam goes to what's called a condenser, which cools the water, turns it back to water. And then that water recirculates and goes, and this is called feed water here, this part of the system, and that feeds the steam generator, and also that has heat transfer so that it cools the water that goes to the reactor. That water then goes and cools the reactor core. And so it's not obviously this simple. There's a lot of indications in this system, but in a nutshell, you have the nuclear reaction, which you control with the number of neutrons that are available with in the system, with the control rods and other ways as well. But the control rods are one of the mechanisms when we're talking about safety. And then you have water that you're circulating to provide cooling and to actually generate electricity. And we care about pressures, levels, flows. We have very complex and redundant control systems to maintain the process. And we have very robust safety systems that are isolated and have a lot of redundancy to make sure that the safety functions are appropriately met. So does anyone have any questions about the basic, how a nuclear power plant works? Because especially the steam generator part, and we were talking about the feed water, which is this pump that provides water to cool the core and also to generate steam. Perfect. Okay, feel free to interrupt with any ad hoc questions. So here's a picture of a typical nuclear power plant control room. What struck me the very first time I had any exposure to nuclear power plant control room, which is how outdated these control rooms look. This is a completely analog system. And there you can see some digital screens. There's some computers that they put in to monitor safety parameters after 3 Mile Island. But the vast majority of the control system is analog. this is a control room simulator, but their control room looks exactly the same. This is Diablo Canyon in California. And we have mostly physical switches, dials, and gauges. And they actually manually turn these switches. Up here we have what they're called alarm tiles. It's literally a box with a light behind it that flashes. And so this is really extremely old equipment. And the vast majority of nuclear power plants in the US look like this, or only with a few upgrades to their system. So why do we care about cybersecurity in these? They're, with electromechanical, they're largely electromechanical. So there's considerably less risk when it comes to cybersecurity. Well, they're planning to upgrade, and this is not intended to be a picture of an upgraded control system. This is our simulator facility at Idaho National Lab. We call it the Human System Simulation Lab. And what we do here is we evaluate the human factors of control system upgrades. And so right now, the nuclear power plants are running into obsolescence issues. They literally cannot find spare parts to their systems, so they can't maintain their system as it is. They spend a lot of money on, tracking down some of their analog components. They have been known to buy things on eBay and also to reverse engineer some of the components so they can simply maintain. And so they're kind of at a point now where they really have to upgrade. And on top of that, they're also at a point where the economics of generating nuclear power are not extremely favorable. And a lot of plants are at risk of shutting down or retiring early before they were scheduled to in their NRC license, their Nuclear Regulatory Commission license. So the impact of that is that they're trying in increasing the economic viability. They have to simplify their operations model, and that simplification relies a lot on integrating new technology and on a lot of new data connectivity. And so it's sort of urgent that we address the question of, okay, so what does that mean from a risk perspective? What does that mean we're addressing the question of how humans interact with these systems in this laboratory. That's the main focus of our work. But similarly, how do we secure these systems? How do we know what the actual risk is? And can the operators cope with the different kinds of complexity that's going to come into the control room? So so what we typically do is we take this is a mock-up of that analog control system. So if you can see, we kind of are imitating these gauges and dials. And we do this we have a lot of different models. So every nuclear power plant in the US is required to have a high fidelity, or an exact replica actually, of their control room. And they have a physical replica that has a very sophisticated physics model underneath it running to describe how the plant's going to respond, and a very sophisticated model of their control system. And so it's basically like an extremely good flight simulator for a nuclear power plant that they can train on. And we take advantage of that, and we use that to do operator studies. And the cool thing about having these sort of digital, this is just a computer with monitors that looks like a control panel. But because we have a digital replica, we can remove stuff, we can move controls, we can put whatever digital interface we want to in there. And that allows us to make changes to the system and test operators on them to see how they respond, where challenges are, whether the interface is well designed, and get that feedback to the vendors who are actually designing the control systems. And it also, another thing that we do is test more innovative concepts to sort of demonstrate how you could really improve the way operators get information by not only replacing something with something that's very similar, which is what the nuclear power plants are doing at this point, but replacing something with extremely consolidated and aggregated information. So this is an example of what how would we go about doing that. This is we have the existing nuclear power plant. We take, when they're going to do an upgrade, we take all of those physical components off the boards. We put a new modern interface on top of that, and then we run scenarios with the old system and the new system and compare how operators do. And so that's just the general that's what we do in this lab. But what's cool about that is that this lab allows us to also test how operators respond to cybersecurity scenarios. And that's what the bulk of what I want to talk about is today. So one of the things that, as I said early in the talk, I study how we evaluate risk for nuclear power plants. Nuclear power plants all have what's a PRA, a probabilistic risk assessment, that they use to evaluate safety. They typically do that by generating what's called fault trees, where it's Boolean logic, where you say, okay, if this component fails, you have a probability of that component failing, which comes from industry operational data and also the vendor data. So the vendor tests the pump to failure, so you have a probability of a failure, and then you also have feedback to that probability from operational data in the industry. And so that's really good information about the failure of those components in the operating environment and also just in the lab. The challenge is that if you put computer security into that, it becomes essentially a manageable problem. It turns a manageable problem into an extremely unmanageable sort of infinite set of possibilities. So modeling failures due to cybersecurity, you don't know you have to know all that context that we talked about in the house. Who's attacking me? What can they do? Can they pick my lock? Can they bust my door down? Do they have a tank? And you have to know, okay, what is my resilience of my system to actually to that kind of attack? What physical impact is it going to have? You have to know all of those things. And so modeling those failures is extremely challenging, just determining what can happen. And then a key part of this is knowing the probability that a particular component will fail, and so the likelihood that something will happen is extremely challenging and close to impossible, I would say, because you need data for that. And it also has to be a stable enough situation for which your data actually applies. And I think that's where the real challenge is that the probability, the frequency that a certain attack has occurred today is not necessarily going to be valid in 20 days. And I think we're not going to be able to use historical data to really predict accurately what the likelihood of an event is in the future when it comes to computer security, because there's a lot of factors and it's really fast changing technology, fast changing capabilities, and threats are evolving. So the approach that we have decided to take as a first step in some of our research is focus on the physical system. Don't worry about how an attacker might get in, and sort of just model the physical system in a way, but look at it from sort of an adversarial, if I am trying to sabotage the system, what could possibly happen given that the components are structured this way and the control logic is structured this way. And in our work, we've allowed extremely special consideration for humans because they cross physical barriers. So we've been focusing on what we call corruption of information flow. So if you have a sensor that's providing feedback to a controller, so if you have a valve that is going to open or close to maintain some flow, you need to know what the flow is. If you have a sensor that's telling you what the flow is, what happens if we send the wrong information? What happens if the controller logic is bad? So we sort of evaluate all those different things, and we sort of focus on what we call the dotted lines, which in these system drawings are typically represent information going from point A to point B. And when you talk about a nuclear power plant and many other systems, we talk about different levels of protection. So you have in nuclear, in some definitions, we have level 4, which is the most protected state, where you only have information going out. You do not have information going in from lower levels. And so you have one-way communication. You might have a data diode here. You might have firewalls at different levels, but you're essentially saying this is the level where the most important stuff happens. This is like the business network where expect people to be connected to the outside, the internet, or whatever. And the important thing is that you have humans who cross all of these, what I'm calling technical barriers, which are if you have data diodes or firewalls or other things in place, or you simply don't have any connection at all. the humans are crossing this entire barrier. So anything that the human sees here on the business network could influence their behavior when they're interacting with the control system or the safety control system at this level. And I think that's people kind of ignore that because it's hard to characterize. And I think it's more important than people treat it. So I'm going to describe, did I hear a question?
No, we're good.
Okay, thank you. I'm going to describe two studies, full-scale simulator studies that focused on operator response to corrupted information. And I'm going to give a disclaimer because in experimental psychology, I always joke that psychologists are the smartest scientists because we work on the hardest kinds of problems, and we have to be super clever about how we manipulate and how we design and control our experiments so that we're sort of eliminating variables that could explain our results. So alternative explanations so we can actually answer the question that we're trying to answer. And in these cases, these were not they were not controlled experiments because we only had one operating crew. So we didn't have, we controlled the context that we were surrounding in, but we didn't have multiple crews. This is not representative of all of nuclear power. It's not even representative of the specific power plants that we were testing under. And so these are meant to be qualitative insights that will help sort of drive future research. And although I think there are important insights that we can draw from this and think about, they're not generalizable or representative. And so I just want to make sure that that's clear. So the first study I'm going to describe is actually performed by some colleagues of mine. Ron Boring was the lead of this at Idaho National Lab, and it was done in coordination with Sandia National Laboratory. And they were using some cool modeling technologies to essentially look at exactly the problem of corruption of information flow. And they essentially took, so these were, the other piece of this that's interesting is that we did these studies on analog systems, even though we're mostly interested in digital systems. And what we told operators in both of these studies was that we had a behind the boards upgrade. So that has actually been proposed and actually implemented in some cases for specific systems where the interface to the operator still looks like an analog control system, but the actual control system is digital. So behind the control boards, it's digital, and in front of the control boards, it looks analog. And so that was the sort of the story we told operators. And we didn't prime them. We didn't tell them that they were going to have cyber security type failures. We just brought them in and told them that they were going to be operating. And the cool thing about working with operators is that since they train in the simulator extremely commonly, or frequently actually, so every 6 weeks they're in a training simulator, they take they take the whole scenario extremely seriously. They treat it like they're actually operating a nuclear power plant. And so we get some realism that we wouldn't get if we were doing scenarios with student populations. We were doing studies, but operators are really conscientious and they take these situations very seriously. In this study, they essentially said, okay, this is how this many digital controls were implemented on the system, and then they sort of took a sample of those controls and randomly said, an attacker has access to these, and we're going to spoof the indications. And so they, spoofed some indications and not others, but they didn't make concerted attempts to mask the indications. So they, the operators had additional redundant indications. They didn't look at, okay, what is the operator going to look at next to validate that this information is valid? And so what they found in the study was that the operators were extremely resilient to these spoofed indications, and they did 9 scenarios, and in all 9 of them, they successfully brought the plant to a safe state. And what a safe state typically means is that they either totally isolate the system that they have a problem with, or they shut down the plant, which means tripping the reactor. Tripping means we put those control rods in and shut down the nuclear reactor, and started cooling the plant to ensure that it's in a safe state. And one of the cool things that they did in this study was that they used eye tracking, which is something that we typically use. And what they found is that there was strong evidence that the operators would look at, they'd look at the indication, and then they'd immediately look at the redundant sources of input. Sometimes if you have like a valve that's supposed to be open, but it's closed, but the system response isn't what you would expect, you look downstream to see if there's flow there. You look at temperatures and pressures to see if they're responding in the way that you want, because it's a very interconnected system. There's a lot of information, you have a lot of gauges and dials. And so even if your indication is false, you're gonna have something to rely on, assuming that it's not all compromised, to validate that the system's responding appropriately. I think the interesting thing in this study is that the operators never suspected cybersecurity as an issue, and that may be because they were looking at analog interfaces. But I think it's more related to the fact that the operators are actually tested on instrument failures and sensor failures routinely in their training. And so they're used to having a sensor say that it's one thing and have the system respond. And sometimes, when the sensor failures or the instrument fails, the control system will respond, and they have to go ahead and diagnose that that's a sensor failure and figure out how to fix things. So they're used to getting some of this sort of false indication and responding to it appropriately. And so the question then is like, okay, is cyber spoofing any different in this case? And so that's a question that we can discuss at the end if you want. So in this case, the bottom line is that the operators detected a problem and took actions to get the plant in a safe state in this study. And I want to remind you that they assumed in this case that the system was, or that the attacker was just randomly changing things and didn't necessarily know what to change to really fool the operators. And so we did a study to look at what would happen if you were really trying to fool the operators. And we did several scenarios that were, we did 4 scenarios, and they varied in the complexity and the amount of things that we were doing. And this is the most interesting of the 4. This is a schematic here of control for the level of that steam generator. So we have this controller that is controlling the feed water reg valve, which opens and closes to maintain the level in the steam generator. So we have a flow transmitter that serves as an input. We also have this, it's taking a lot of different inputs to calculate not only based on the flow, but on other indications, what the actual position of this valve should be to maintain this level. But this piece of it kind of lags behind the flow. So the flow is like the top level signal. And then we have this more complicated calculation that serves as input, but it doesn't happen all that quickly. And so we're trying to maintain 57% in the steam generator. We have 4 channels to tell us what the level is in the steam generator. We also have 4 channels to tell us what the flow is in the steam generator. And we have indication of how open or closed this valve is on the controller itself. And this controller all of this stuff is on the control screens, roughly in this area in the power plant simulator. So what we did, sorry, I keep hearing little, did I get a question?
No.
Okay, perfect, sorry. So the interesting thing here is that we didn't, in some of the studies that they did in the previous one and some of our studies, we actually injected failures that would cause the control system to do something, which is what people are most scared of, right? They're like, okay, what if someone gets on my control system? Is the operator going to be able to respond to that? And in this case, we only spoofed indication. We did not have any control failures. And so had the operators done nothing, the plant would have remained in a safe and operable state. And the other interesting thing is that we spoofed, there are 4 channels, and one of them is the control channel, the channel that serves as input to the controller. This is not necessarily representative of how a digital system would work, because it'd probably be some sort of average or combination of multiple channels as a control input. But in this case, it's one of the channels as a control input. And we spoofed 3 out of 4. We left the control channel completely alone. So, and we did the same for the flow and the level, and we spoofed what the output of the valve was. So we made it so that we were lying about how open this valve was and how much water it was providing to the steam generator. So it ended up, so the operators had the right indication in both cases, and they knew which channel was actually providing the control input. We also spoofed an alarm, and this may have been one of the most influential pieces of it. So we had an alarm come in that said that the level was low on the steam generator. And so what we basically said was we made it look like level and flow were low in the system, and we wanted to see what the operators would do. What the operators did end up doing in this case was taking manual control, because this is typically in an automatic mode, and increasing the output of the valve so that it would then send more water to the steam generator, because they thought, based on 3 out of 4, that this was too low and that the flow was too low. They added more water to the steam generator, and ultimately what happened, and it happens very quickly, the power plant tripped, it shut down. And I think the important thing there is that this is still not a safety situation. We didn't cause damage to the plant, we didn't cause harm to the public, but we did cause a situation. The operators caused the plant shut down, and when the plant shuts down, it's millions of dollars a day before they get back up that they're losing, and that's a huge economic impact just to have an unplanned plant trip. So again, we didn't have any malfunctions. We only spoofed what was indicated to the operators, and the operators had plenty of redundant indication to tell them what was really going on. But the reason, and this is all about the assumptions we made, that the operators responded this way is we understood their training and we understood their procedures. So we used like their procedural, they have extremely specific step-by-step guidance that they have to follow. They're trained to follow it word for word, and only use outside their own operator judgment when they think it's absolutely necessary to maintain the system in a safe state. And the other contextual features is we chose feed water because feed water is one of the systems that has been upgraded to digital systems across many plants. It's one of the more common digital systems in nuclear power plants today. And digital feed water is one of the main causes of unplanned plant trips, which is a shutdown to maintain safety in the US. And so operators, as a result, are used to having this experience where they're saving the plant from an unplanned plant trip if they can act quickly and resolve this issue. And so it's sort of informed by an existing problem that they're having and that they have experience resolving. And there's sort of this, this pride of being able to prevent this unplanned plant trip in this situation. And so this is all context that we used to we were trying to say, okay, if we were someone who was planning to cause harm, how could we do it? And I think taking that perspective leads you to different conclusions. And so we're playing the role of a very sophisticated saboteur in this case, who had access to all the information they needed. They understood the system design, they understood the procedures, they understood the operator's experience and training. And so that's a very different context than someone who just has opportunistic access to the system and is randomly changing things. And I think what's interesting is that we did this scenario with failing 1 out of 4 instead of 3 out of 4. And they were able to mitigate the situation and bring the plant to a safe state and understand. And I I haven't validated this, but this is something that I'd like to explore in the future, is that is there some psychological bias to say, okay, when I have 3 out of 4, the majority is the more, is the real indication, and the, you know, when it's the minority that's spoofed, I'm gonna discount that and trust the number that is the majority. And so that's something that I'm going to look into in the future to see if that, because that might be an interesting insight to how, you know, how redundant you have to, how many redundant indications you have, and guidance for the operators when they go double check stuff. Any questions at this point about the actual study?
No.
Okay, so I'm towards the end of the talk, and there'll be plenty of time for questions at the end. This is just one example of the research that we've done. I wanted to be able to go into enough detail so that you guys could actually follow what we did and why we did it. And so there's a lot of stuff I had to provide as background. But the bottom line is that, you know, the 2018 study assumed we had sort of an unsophisticated attacker, still sophisticated enough to get into the system, which is an important thing to consider, because you know, the question of how you would actually get into one of these systems remains not unexplored, but it's not clear how resistant these systems are, how actually air-gapped they are, whether the security controls that are required, especially for the digital systems, and especially as we move into the future and upgrading these, what those actually how we will get in, how vulnerable they are to attack. So that's an important piece that we didn't address at all in the study. But the 2019 study assumed a sophisticated attacker with detailed knowledge of the procedures, systems, and training. And this, you know, while this might seem extremely unrealistic, I think when we're talking about critical infrastructure, it's my opinion that we have to assume that we have that kind of attacker targeting our systems. Maybe it's not nuclear power, maybe it's other systems, but we have to assume that we have extremely sophisticated, highly resourced attackers who have an interest in disrupting our operations. And I want to highlight all of the cases. Power plant ended in a safe state. So even in the one I just went over, public safety is always the #1 priority. And so we always characterize things in, did we shut down the plant? Are we releasing radiation? Are we protecting the public? And did we damage the fuel? Because damaging the fuel results in that's one of the more risky kinds of situations that you can end up in. And so that's, you know, the context that we work in, but I have been interested in the economic loss if we're talking about maintaining the nuclear industry, because we need the energy that's provided by it in the United States. We need to also consider, you know, the reputation risk if something happens in a nuclear power plant. Having a plant trip because of a cyber intrusion would be extremely damaging to nuclear power as a whole. So that's something that we have to also consider if we care about maintaining the nuclear industry. And as I said before, operators are extremely used to handling misleading information. They have sensor instrument failures all the time in their training and in the real plant. And so they're actually used to, they're very well trained at saying, okay, my indication is telling me something that doesn't make physical sense given how I understand how the system works. And I need to figure out what's going on so I can make sure the plant is operable. And so they may be extremely resilient to spoofing kinds of cyber attacks, with the exception of, you know, if you had a digital system that gave them information and you changed the pixels on the monitor to show them that something was happening that wasn't, you might be able to essentially prompt them to take a bad action on the system. And that was what the question that I wanted to answer with our study.